Alright team, today we're diving into one of the most fascinating and powerful components in electronics, the capacitor. Think of capacitors as tiny energy tanks. They don't store energy the way a battery does, but they charge and discharge incredibly fast. This makes them super useful for quick bursts of power, energy smoothing, and even signal processing in circuits. So, how do capacitors work and why are they so important? Let's break it down step by step. Imagine you have a water pipe with water flowing through it. If you shut the valve, water stops flowing altogether. But if we add a water tank in the middle of the pipes, the water tank fills first, then water flows out. The key idea here is, even if you turn off the source water in the tank, it still flows briefly. In a circuit, the water tank is the capacitor. So we had a simple circuit with a switch to a battery. If you flip the switch on and off, the LED turns off immediately. Let's add a capacitor. When the battery connects, the capacitor charges or fills up. And when you remove the battery, the capacitor discharges and powers the circuit briefly. With a capacitor, your LED doesn't blink off immediately. It stays lit a moment longer. So capacitors smooth out electrical interruption. Great, so we know what a capacitor does, but what is a capacitor? It's made of two conductive plates and a dielectric insulator in between. In a ceramic capacitor, you have two metal round plates called electrodes and a ceramic insulator sandwiched between those two electrodes. Think of it like a peanut butter sandwich. The top slice is one plate, the bottom slice is the other plate, and the peanut butter is the insulating dielectric. Can you tell I wrote this when I was hungry? During the charging phase, when we connect a capacitor to a battery, electrons build up on one plate and the other plate loses electrons. And so the capacitor stores this energy in between those two plates. And this goes back to one of our very first lectures on static electricity. The capacitor stores the energy in an electric field, and that electric field is created from an electron imbalance. One plate lost electrons and one plate gained electrons. And as we remember, opposites attract, so they're always attracted to each other, but the dielectric keeps them separately. So this energy is always stored in the electric field. An electric field is what charges create around them. Positive charges make electric fields that push energy out. Negative charges pull energy in. When you have them next to each other, they draw each other closer to one another. It's the invisible push-pull between opposite charges. Because we know opposites attract, the plates are always drawn to each other, but the dielectric keeps them separated, creating a constant pull. With extra electrons on one plate and fewer on the other, the space between fills with this field and the capacitor stores energy in it. A capacitor will charge until it reaches the voltage of the battery across the two plates. Once the capacitor reaches the voltage of the battery, electricity or current will no longer flow. Say we have a 9-volt battery and a capacitor. Once the capacitor matches the battery, there's no voltage difference, so current stops. If both are at 9 volts, the difference is 0. Current only flows while the capacitor's voltage is below the battery's. To discharge a capacitor, you first have to disconnect the battery. The stored charge flows through the circuit from the capacitor, and the LED stays lit until the charge runs out. Now that we have a fundamental understanding about what a capacitor is and how they work, let's talk about the math behind them. Let's introduce some equations to describe how capacitors behave. The main equation for a capacitor is C equals Q over V, where Q is the charge in coulombs, C is the capacitance measured in farads, and V is the voltage in volts. Just like resistors, capacitors can be combined in different ways in series and parallel. When capacitors are in series, it's very similar to when resistors are in parallel, where the equation is 1 over C total equals 1 over C1 plus 1 over C2 and so on. and the total capacitance is less than the smallest one. Capacitors in parallel, on the other hand, behave much like resistors in series, where the total capacitance is just the sum of all of the capacitors in parallel. Cool, let's bring everything back home. Capacitors are small but mighty. They store and release energy fast. They smooth out voltage changes, and they power flashes and detect touch. Their behavior depends on how they're wired, series or parallel. Next up, we'll explore how capacitors and resistors work together to create timers and oscillators. Take a picture of your circuit and tag us at Horizon Robotics Lab. See you in the next one. If you like what you've seen so far, you should visit our website and check out our electronics and coding kit. It comes with all the videos, all the lessons, all the code, all the labs, and all the project files. So yeah, link in the description and happy learning.